Okay, so here I'm just going to run through LabScript 5. So this script is about using correlation and some basic data visualization in R. Now, as with the previous script, first thing we're going to do is load up tidyverse. So really, really important at this point that we always just run this line and load it up. Now, there we go. So we can see it's attaching these packages. And in particular, the one we're going to need today is this one, ggplot2. This is one of our data visualization functions in R. Now, if you've gone to the page for this, you'll see there's actually two data sets. So we're going to be using this one, which is the one from the previous lab script. So the Scottish Index of Multiple Deprivation. And then at the end, with the bonus material, we're also going to be using this codebook for voter fraud in England in 2019. Now, if we come back over to R, we can see again we've got this code for just reading in the data. So the first thing I'm going to do is going to check my working directory, and you can see this is defaulted to documents. Now, I've already downloaded this data, so I'm going to use the same method that I showed you in the previous lab, which is coming up here to session, set working directory, choosing the directory, and then if I come over here to where my directory is, so I put this data in this one, click open, and you can see it's run that line there. Now that means I can actually already run this. So if I run this, you can see the data's loaded in here already. But if I wanted to, have this code so that I could repeat it whenever I want, I can always copy it in up there. And actually you can see that's nicely formatted now as well. I don't have to go through the stage of replacing these backward slashes with forward slashes. So I'm going to skip glimpse this time. Although, again, if I'm being asked to check data, and if you're being asked to check data in assessments, you've always got a glimpse here to do it. And then I'm also going to go through this stage that we did last time of just cleaning up my data by replacing these stars with system missing. And again, this is because in this data set, the missing values are represented by these stars. So if I run this then, we can see it's run down here. So if you don't see errors coming up down here, it usually means everything is run fine. And if I want to check that, I can just come over here, come to one of these bits of data that I know had some stars in it. And you can see all of this has changed all at once to system missing. So what I'm going to work on today then is this section on correlation, this section on scatter plots, and then also down here in part 2, which I think we didn't get to in most of the labs, we're also going to look at creating some new variables by recoding the existing variables. So correlation then, this is something which has sort of been described on a statistical, mathematical level by Hannah in the lectures. So back here in lecture 4, Hannah talked about bivariate associations. So when we have two variables and we want to know how much of the variance in X is explained by the variance in Y, we actually have a lot of different options to do this. But one of the ways we can do this is what we call correlation. And there are different ways we can calculate this, but the most common one is to use this Pearson's correlation coefficient. And what we get from this is a number between 1 and -1, so 1 being a perfect positive correlation here, -1 being a perfect negative, and no relationship at all between these variables being scored as 0. Now, to do this, we need two numeric variables. And as we looked at in Lab 4, when we read in variables, they aren't necessarily matched by the correct vector type automatically. And when we come to using the actual code in R that calculates a correlation, we need the vector types to be numeric. So what we're going to use then is, firstly, we're going to check the class of these two variable types. So the relationship we're going to be exploring here is that between misuse of alcohol and prescription medicines, particularly for mental ill health. So this is the kind of theory we might come up with as social scientists, because we might think that either higher levels of mental ill health lead to higher levels of alcohol misuse, or vice versa, right? Now, how we disentangle those two is a much more complicated question, but at the very least, we would expect those variables to be correlated if they're related. So in our data set here, we have these two variables. So I'm going to check the class of alcohol and depress. And if we come over here to our codebook, we can check how these are defined. So in this case, alcohol here is our standardized ratio of hospital stays related to alcohol misuse. Now, this is a value of 100, indicating the average for data zones of the same age and gender profile. So it's a sort of variable that's already had some things done to it, and it's what we call a standardized ratio. Down here, we've got depress. Depress here is the percentage of people in that area prescribed certain kinds of medication. So these are actually different kinds of variables then. So we've got a standardized ratio on the one hand. This could actually take any value from 0 to infinity, depending on the level that's measured here in terms of stays related to alcohol misuse. This one can only take a value between 0 and 100. But nonetheless, we can still calculate a correlation here, so long as they are both numeric variables. Now, if we come over and check these then, so I'm going to use class here rather than type of. If I run these, we can see these have both been read in as characters. And of course, the reason for this is because they clearly had some missing data in there, indicated by those stars. And for that reason, the entire variable has been classified as character rather than numeric. So I'm going to use this same style of block of tidyverse code here to change this. So we looked at this last time, so I won't go over this again specifically, but what you can see is we're using this mutate function, and within that we're embedding code that changes alcohol to a numeric version of itself and depress to a numeric version of itself. Now, in this case, we've already changed everything to system missing by running this. So when we run this, hopefully we shouldn't see any of those errors that we saw last time. So last time we had this error, NA introduced by coercion, or I shouldn't say error actually, it's just a warning. So a warning means it does work, but it's giving us a warning. But this time we shouldn't expect to see any warnings because we've already changed all of the stars to system missing. So if I run this, we can see here that we haven't got any errors here. Now if I come back up and run these again, so same two lines of code up here, these have both been changed to numeric. So this is why we need to do this sort of data cleaning process in advance of running code or running analyses that require certain things. Because if I'd run this next couple lines of code while this was still a character, I'd have got an error. It would have told me it's the wrong variable type to be running a correlation on. Now, this is again where we sort of, in some ways, find that the code is less complicated than the calculation we're running. Because, as Hannah went over in the lecture, we've got various stages to calculating this correlation coefficient. So we have to look at the covariance and the standard deviation of both variables. And this eventually, through a kind of series of transformations, leads us to this number. In R, though, we just have this one simple function. So we've got COR here, correlation. And we're then putting in our two variables into this. Now, if we want to run the help file for this, so help files are, again, something we looked at when we were looking at memes. And again, I looked at this in week 4 as well. If we run this, what we'll see is that correlation, variance, and covariance all have the same help file. And because they're examples of the same kind of calculation. So we call these matrices. So here's correlation then, and we get our usage example. And what we can see is that we need an X and a Y variable. So we need to correlate something with something else. We've also got these options that also have defaults, and we'll come to this in a second. So this is a complete function then. So we've got Rx. So Rx down here is SIMD extract alcohol here. And our Y is SIMD 2020 extracting depress. However, if we run this, we're going to get an interesting result. So if I run this, you can see there's no error down here. So it's delivered me a result, but that result is NA. So in other words, the result is missing. Now, the reason why this has happened is because we can't calculate a matrix for variance, covariance, or correlation unless we have complete pairs. So again, if we come back to this lecture and we look at the kind of data that we use to calculate this, we have an X and a Y variable. Sorry, I've lost that in this script, but we need an X value and a Y value for all of these. If we don't have that, then we can't actually calculate correlation. What we can do instead then is that we can actually not use any of the observations that include missing data. Now we can do this by changing this option. So you can see the default option for covariance and correlation is that we've got here use equals everything. So it's trying to use every row of our data. So each and every one of these rows R is trying to use. And if we've got any missing data in any of these, or in the variables that we're trying to use, we're going to get this NA result. Instead then, what we can do is change this option. So rather than using everything, so here in the help file we can use everything, all observations, complete observations, NA or complete, and this is when we're going to use pairwise complete observations. So this is when we have a value for X and a value for Y, and for all the other observations we simply delete them from the calculation. So even though this is a complete function, we haven't got an error here. To get a meaningful result, we need to use this. So this is correlation. This part is exactly the same. We're specifying our two variables, but instead we're saying use pairwise complete observations. And this is what we would usually use for correlation, because again, these matrix calculations, they need complete pairwise observations. And if we run this, there we go. Now we've got a sensible number for correlation. So as we have here, so between 1 and -1, we've got a result that sits around here. It's 0.56. So we're in weak positive correlation between these variables. So 0.56 here. Now, the other thing we can calculate, and again, Hannah talks about this in the lecture, is we can calculate what's called the R-squared. Now, the R-squared, in terms of the calculation, is simply this number squared. We can do this in R with this little hat symbol and a 2. So this gives us to the power of 2, which is the same as squared. So if we run this, we're going to see 0.322. So what does this value mean? Well, the R-squared is generally taken to be the amount of variation in X explained by Y, or vice versa. So our 0.32 here means that we've explained about a third of the variation in this case, the prescription of psychiatric medication by the standardized ratio of admissions to hospital for alcohol misuse. So generally then, when we're doing correlation, we want to calculate this and this. And what you might notice already is one of the other properties of R-squared is if this was a negative correlation, negative correlations still help us explain the variation. And if we square it, this would of course still be a positive number. Now, if we wanted to do this with other variables, it would be pretty easy. So again, if we come down to this point in our code, down below part 1, we've got some space here for you to find some other variables in this, change them to numeric, and calculate the correlation. So I'm going to do that now. So the easiest way for me to do this is I've got some code here that is sufficient for changing the variable types to numeric and calculating the correlation. So all I'm going to do is copy this and bring it down here into the spacer, copy it. Now I don't need this because we know this doesn't work, so I'm going to delete this. And I'm going to find two other variables. So I'm going to come over to the code book, and I'm going to look for some things that I think would be interesting to look at the correlation between. So in this case, I'm going to look at income rate. So this is the percentage of people who are income deprived, and we know as social scientists this is likely going to correlate with a lot of other different social outcomes. So firstly, I'm going to just copy income rate out of here. It's the variable I want to use. I'm going to come back over to R and replace alcohol with income rate. Now it's important that I do this on both sides. Otherwise, I'm going to transform alcohol into income rate, and I don't want to do that. So what am I going to correlate with income rate? I think I'm going to look at this. I'm going to look at not participating. So this is the percentage of 16 to 19-year-olds not participating in education, employment, or training. So this is, again, a slightly different type of numeric variable. It's a percentage. We started off with a ratio, but we might have good reason to think that a large number of low-income households, this might lead to, maybe lower levels of participation in education. Maybe people that age are working instead to help out their families. So let's come in and I'm going to use not participating. So I've swapped that out and I'm just going to run this code. So there we go. Both of those have been changed to numeric. And now all I need to do is the same thing here. So I'm going to change this to not participating. And I'm going to change depress here to income rate. So if I run this, that's interesting. I've got almost exactly the same correlation here. So about 0.56. So there's some positive correlation then in this data between areas with high non-participation in secondary education and high levels of income deprivation. And of course, if I wanted then to calculate the R squared, see how much of this I have explained, I can come over here and I can, in fact, if I can't find this on my keyboard, which again I can't, it's going to get hat2 from somewhere else, come down here and calculate that. So again, about the same correlation as before, so about the same R squared, 0.31. So again, I'm explaining about a third of the variation in non-participation in secondary education as a function of the level of income deprivation in a given area. Now, that's one way then I could represent this. I can represent this with this number, Pearson correlation. But I might also want to visualize this. I'm going to skip over this for the moment and then come down here to scatter plots. Now, the way I would usually visualize this kind of correlation is we might do a scatter plot. And this is the kind of graph that you'll likely be familiar with. When I'm doing graphs in R, though, I'm almost always going to be doing it through this function. So this function is called ggplot, and it actually allows us to create an almost infinite variety of different graphs in R. So let's look at this function. And in fact, actually, I'm going to run this and show you what it does first. So here we've got these two variables we were working with before, alcohol and depress. So this is the relationship we already explored here with correlation. So if I run this, over here in plots, it's going to open up a scatter graph. So that 0.56 correlation, we can now see that represented in our data here. So we've got a positive correlation going on here between these two variables. Not a particularly clear one. Again, that's not a strong result for correlation, 0.567, but we can see that in our data. So why did it do this? Well, firstly, let's look at this bit. So we are using our data over here, so SIND 2020, and then we are piping it into ggplot. The next thing we're doing then is defining what our x and y is. So we're doing that with this little subfunction. So AES here actually means aesthetic mapping. Now, we don't really need to worry about why it's called that, because this is going to be our standard opening. So dataset name, pipe, ggplot, aesthetic mapping, x equals whatever we want our x variable to be. So in this case, it's alcohol down here, and our y value is going to be depress. The only other thing we need to do then is specify what type of graph. And the standard openings for this is this GOM, or GOM, underscore, and then we specify the graph type here. So in this case, point is scatter. And we'll look at various different things that we could replace this with to create other graphs as we go through the latter half of term. So that's what I just ran then, and it created that. Now, that might be good enough then for our own purposes, just to explore the relationship between different variables in our data. The real advantage, though, of ggplot is because I can keep adding things to this to the point where I'm getting a graph where I can really, present this in a publication, in a presentation, in a way that has all of the labels and all of the visualization options I want. So in the first place, I could start doing things like adding some color. So if I add color options to GOM point here, so this is exactly the same code, but with a color option, I start getting things like, now we've got some blue dots. I've also got things like theme options. So you can see I'm adding lines here with these pluses. They work a lot like pipes do, but within this ggplot function. So all of this, we're within ggplot. And if I run this, it's going to add a slightly different theme. So the theme in this case is line draw. There are lots of different themes, but this is the one we're using here. So if I use my line draw theme, we can see we've got a slightly different visualization again. So line draw happens to be a theme that shows white background with these thick black lines. And then I can also finally add some labels. So here I've added another line. Our function within ggplot for labels is labs. And I've got options for the y-axis, the x-axis, the y-axis, a title, subtitle, and caption. So if I run this then, you can see already here we've got a sort of full graph. So I'll click on zoom here, and I've nicely visualized this. So I have a title, I have a subtitle showing the correlation. My X and Y axes are properly labeled, and I've even got a caption down here giving the source, which is the Scottish Index of Multiple Deprivation, and the N here. And if I want to save this out of here, I could always click Save Image. Let's come over to my working directory. And I can save this plot in there. I can also come over here to export, save as an image, save as a PDF. I can copy it to my clipboard. So ggplot then has a few different functions. We can use it to explore our data, but we can also use it to present our data in a way that would work for professional publications. Now, again, the good thing about this is that this code, its structure doesn't change no matter what I put in it. So we were working with some different variables before. So again, I'm just going to copy this. And I'm going to come down to my code here. So before we were looking at income rate and non-participation. So we can do the same thing here. So here's our ggplot from before. But instead, I'm going to put in income rate and what was it, non-participation? What have I got that wrong? Yeah, not participating. So I'm going to take the variable from here and put it in as our y here. So for the sake of argument, I'm going to change the color. I'm going to change this to red. So whenever we have a recognized color, we can see it comes up here as the recognized color. I'm going to keep the theme as line draw. But of course, we need to change these labels. So my X is now income rate. So let's change that label by coming over here. And there we go. There's our definition. Percentage of people who are income deprived. So I'm just going to copy that into here. And our Y is this not participating variable. So let's come over here. And let's find non-participating. Where's this? There it is, non-participating. So percentage of 18 to 19-year-olds not participating in education, employment, or training. So I'm going to change my title as well. So by very association of income deprived households and non-participation Now I'm not putting in capital letters here. I probably should be, but I can come back and change that later. Now my subtitle before my correlation, and for this it's slightly different. It's actually 0.56. So let me just change that. And actually, I'm going to put in my r squared too. So I calculated that. So my r squared was 0.32 if I round it up. And this actually is the same. So we're still using the Scottish Index of Multiple Deprivation. And there's our n. So if I run this now, so all I've done is changed out the labels. I'm going to change the color. And I've changed out the variables. So if I run this, there we go. There's our new correlation. So this looks a bit different. But you can still sort of broadly see that moderate positive correlation between income-deprived households and non-participation in education. So again, I could extract that straight from there, and I've got a reasonably well-presented graph showing the relationship between these two variables. So this is a good lesson overall then, that really what we want to be doing most of the time with code is, rather than writing it from scratch, we take an existing block of code that we know does a particular thing, and we let things like R's autocomplete here complete this for us, and it reduces errors, makes it a little bit easier to understand what we're doing, and ultimately makes coding a little bit easier than trying to start from scratch. And this is a good thing to notice when it comes to assessments. So all of your assessments for this course, they're all open book. So you have all of this code. And often what you'll need to do is just find where we did something similar in one of these labs, copy the code out of there, and modify it for whatever data set, whatever variables, and whatever kind of analysis you want to do. Okay, so the final thing we're going to look at then today is this part 2 here, which is about recoding variables. The last part here is just saving this as a PNG. So we can use code to do this, but equally we can come over here to export. This maybe is a little bit easier. This is another one of those things that RStudio helps us to do. But if you want to dig into what's going on here, we're using this PNG save function to save it straight from the code. So this is the kind of thing we'd want to do if we're trying to reproduce the same graph every time. So say you do this if you're doing sort of academic peer-reviewed publications, but we've always got this export option over here too, which is probably a little easier to use for the purposes of what you guys are doing. Now, this is going to involve our second data set, and actually I don't need to set my working directory again because I already put VF England CSV in that same data set. Or in that same folder, rather. What I am going to do, though, is I'm just going to clear some of this. So remember, we've always got these little brushes here, here and here, and also here, that I can use to just sort of clear everything off my screen if I want to start working with a new data set. So I'm actually going to do that. I'm going to clear my plot history. I'm going to clear the data out of here, and I'm going to clear my terminal. So I've got a nice fresh slate to start with here, here, and here. So if I read this in, there we go. It's read in. So we see what this data set has: 2,034 observations of 8 variables. And this data set, what's this about? Well, let's look at the code book again. So we always want to be looking at the code book to understand new data sets. So this is the voter fraud in England data set. And we can see we've got various different variables on here. And the important thing is here, a lot of these are categorical. So in our previous data set, a lot of these were numeric. Here, though, we've got things like these strongly agree to strongly disagree metrics. Now, you might know already these are called Likert scales. Now, very, very common way of measuring agreement and disagreement in social science. So people are asked to select one category. So these are questions about how much you agree or disagree with a given statement. In this case, voter and electoral fraud is a serious problem in UK elections. However, when we get those kind of scales, we might think, well, what if I want to create something that doesn't have these 7 categories? This is a bit unwieldy. What if I just want to create 2, say, reflecting agreement or disagreement? Well, this is another thing we can do relatively easily. And we can do it with another one of these conditional functions. So we looked at conditional functions before in the context of creating or of creating a block of code which removes the missing data as stars and turns it into something else. Here, though, we've got another one. So this is another really, really useful function. So this function is called if-else. So again, these kind of conditional language, if-else. So what's this doing? So what we're going to do here is create a test that creates a new binary variable. So in VF England, another thing we've got here is we have variables for age. So here's age, and age is, as you can see, an integer variable. So this is just the exact age of respondents. And again, the data set's going to define it the same way. So yeah, age of respondent in years. What if, though, I wanted to create a variable that instead told me not the exact age, but whether someone was 50 or over? Well, this is what if-else allows me to do. So if I come up here to the help file for this, so here's our option to go to help. You can see what if-else is conditional element selection. And if-else has a pretty simple general structure. So we have if-else, we have the test, we have what we code the new variable if it's yes, and what we code the new variable if it's no. So in this case, what we're going to do is say if-else VF England, so this is our data set, and is the variable age greater than 49? So 50 or above is greater than 49. If that happens to be true, so yes, we're going to code the new variable as 1. If it happens to be false, we code this new variable as 0. So we're creating a binary variable out of a continuous one. Now, in this case, we also need to create a new variable. And if we use extract here with a variable that doesn't exist yet, so if I come over to this, you can see all we've got at the moment is vFalter, vProblem, age, sex, education, Brexit vote, vote 2017, and PID. Let's see what happens if I run this, though. So I'm running if-else, if age is over 49, B1, if it's not, B0, and here's our new variable. So if I run this and come back to my data here, here's our new variable. So we can see we've gone up to 9 variables here. And in our variable, we've got over 50. So 1s, 0s, 1s. So we've created a new binary variable out of age. And another interesting thing, right, is that if we then calculate, say, the mean of this variable, so the mean of this over 50 bin variable, we've got this, 0.49. So the interpretation of this then is if we calculate the mean of a binary variable, that is the percentage of one or the other. So in this case, it's exactly 50% of the sample, well, 49.6% of the sample is, in this case, over 50. And this is also backed up by calculating the mean age. So the mean age is almost exactly the same. So 49.53. Now, we can also keep using this, interestingly. So in this case, we've got another test here. So here's our if-else test. What if we wanted to know how many people in a data set were below average age? So this is our new data, or new variable that we're going to use for this, below mean bin. And this time our test, so here's our test. Here, our test is VF England age less than the mean of VF England age. So this is our whole test here. So is the age of an individual observation below the mean of the same variable? And again, we've got the same outcomes here, 1 and 0. We're sorting into binary variables. So again, now we've created a 10th variable here of whether it's below the mean age. And you can see this is kind of almost inverse to the last one because the average age is around 50. So for the most part, if you are below the average age, you will also be, or if you're not below the average age rather, so 0 here, you're also likely to be over 50. So we can use if-else in a lot of these different ways. And another thing we could do is to come back to our original point here. We can also specify, for example, this in terms of categorical variables. So now this is a table. So we're actually going to come to this mostly next week. But if I run this table function, I'm going to get a table of all of the options here. So we've got agree 167, disagree 245, either agree nor disagree. We're getting the individual numbers here. What we've got here, though, is we're using if-else. So again, here's our test. So our test this time is if VF England V problem is either strongly agree or strongly disagree. So this vertical line here is an OR, a logical OR. It becomes 1 or 0. So in other words, we're creating a variable here which tests anyone who has strong preferences on this. So strongly agree or strongly disagree. So if I run this, and then look at the mean of problem bin, so we can see around 12% then of people have some strong opinion on this. And again, all of this code is modifiable. So let's instead, I'm going to create some new code here. So this time I'm going to look at who agrees. So we've got strongly agree and strongly disagree. But this time I'm going to change this to agree. So this time I'm going to have problem agree. I'm going to create a new variable here. So if I run this, it's going to create a new variable called this. I change this from bin to agree. Change the two ORs from strongly disagree to agree. Let's run this. Again, we can see this is run without a problem here. And I'm going to run the mean of, this time we've got, what did I code it to? Problem agree. You can see it's coming up there, right, as an autocomplete. So around 15% then fall into this strongly agree or agree category, because I've created a new variable that when I calculate the mean, it's going to tell me the combined percentage of both of these variables. And again, we could do this all in one block of code. So this is what we call the base R way. And here we're using mutate, again, this very flexible function to do this all in one block of code. So we're using multiple if-else within our mutate function here. So if I want to create a new binary variable, then I sort of already did up there. But let's say, for example, let's pick some other ones. So I'm going to, again, copy this from here. Let's do strongly disagree this time. So in this case, we're going to get strongly disagree. I think it's disagree. And disagree. Put my caps lock there. And make sure I'm creating a new variable here. So we'll have disagree. So let's run that. Again, don't seem to have got an error here. So let's also grab mean of agree here. And again, we can just change this to our newly created variable, which is disagree. So there we go. There we go. That seems to be 17%, 17.5%. So overall then, 15% of people agree that voter fraud is some sort of problem, and 17% disagree. So we've aggregated both those categories now. And we've done that by creating these new variables that only reflect if people strongly disagree or disagree, and strongly agree or agree. Okay, so the bonuses here involve the Pokemon data. And we're actually going to go through this next week. So I'm not going to record this in this lab now, but do have a look through this if it's useful, because we're going to deal with tables and proportions tables in lab 6. So again, see if you can do the same thing I've been doing here, which is taking this code and modifying it to do your own things. You'd probably definitely going to be noticing, so if you didn't make it to the lab, I think I emphasized this in all the labs, we're definitely stepping up a level of complexity here. Hopefully these run-throughs kind of allow you to sort of pause and see what I'm doing as I go through. And do remember, of course, you don't just have the labs and this. You can also come and see me in office hours if you need some advice. And we're already getting here into what is really for later on in the second assessment. But some of this stuff will also be on the midterm in a week. So I will see you all in labs this week, and we will build up to that first and second assessment.